This video details the final practical product produced from my honours project. This is part of the audio technology course at GCU. I was tasked to critically research and analyse an area that I'm interested in and produce some bespoke work while writing a dissertation about the process. I decided to focus on game audio design and implementation, specifically the simulation of dynamic acoustic effects within 3D virtual spaces, and I did this using a hybrid approach. This project at its current state specifically tackles absorption and diffraction that is reactive to dynamic environments, but this has room for development to accommodate other effects and further optimisations. First, I'll give a quick rundown of the project setup. This is all programmed in Unreal Engine 5 blueprints and uses Fmod to assist in sound playback and manipulation. These are connected using the Fmod integration plugin for Unreal Engine. In Fmod, a simple loop is played back for testing. What's important here is the parameter sheet and its automation. This parameter is named Occlusion and is controlled by a value determined within the blueprint script. The higher this value is, the more occlusion is applied to the Fmod's event. So within Unreal, in the blueprint script, there are many functions that are called to calculate this occlusion value, but the two main logic systems are an advanced line cast system and an A-star pathfinding system. A brief overview of how these work. The line cast system traces a line from a sound source towards the listener position. In this case, that is the blue sphere towards the player's head. And this trace returns a hit result. This hit result includes information on if an obstacle is hit, its distance, and the physical material of that obstacle. These are all factored in when calculating the occlusion parameter value. Next, the pathfinding system uses the A-star approach. This makes use of a 2D grid map and a tile set to determine the shortest path towards the listener. The way it does this is by using custom collision trace channels to detect what objects occupy each tile slot, and cost values are given to each tile depending on this collision. So obstacles have high costs and empty space has low costs. This means in the algorithm the empty lower cost tiles are more favourable to be chosen as part of the path compared to occupied higher cost tiles. There are periodic tile map updates to account for dynamic geometry, and once changes have been detected, the path algorithm is run. Once the shortest path has been found between a source and a listener, the system outputs data to be used in the parameter calculation. Most importantly here is the path's length. Now that this hybrid system has collected all the data it needs, the calculation function can run. As mentioned, the direct distance, physical material, and A-star path length all have major contributions to the final occlusion level. These variables determine the complexity of the geometry surrounding the source and listener, and then certain parameters are weighted more heavily based on this. So in the context of complex geometry, the system determines the A-star path length has a more accurate sound travel path than the direct line distance. This results in a more accurate occlusion level. This calculated occlusion level is sent to Fmod to manipulate the audio and give it the desired effect. And here are some examples of different locations testing this system.